In exercise 1b, we will talk about activation functions. First, we'll draw the sigmoid, the hyperbolic tangent, and the value activation function. And then we will see what happens if we pass certain values to these activation functions. So these values would be the weights times the inputs plus the bias. So weight times inputs summed up plus bias, that's the should be such values that will be passed to the activation functions, and we will see how they transform the actual values. And then we will talk about why we use these activation functions in the first place. So let's start with the sigmoid activation function. This has kind of an S shape. So it converges to 1 at the one side and then converges to 0 at the other side. So basically that's should be very close to 1, and then it passes, should be more like an S here, and passes 0.5 here, then it turns around and converges to 0, but obviously never crossing here or being tangent to 0, just being converging very close to 0. So here's 0.5. And now what we use this for is basically we won't have an output between 0 and 1. So let's maybe draw the other ones and then note down the functions. So this would be the hyperbolic tangent function. And that's a lot like the sigmoid function. You could think of it like a variation which goes from -1 to, or from -1 to 1, and crosses the y and the x axis at 0.0. So here it converges to 1. It should be maybe more steep here even. And then it does the opposite thing here and converges to -1. So let's say, or I'll draw this later. Maybe the ReLU function next. So ReLU, or rectified linear unit, is pretty simple. So every value below 0 is equal to 0, and then every value above 0 is exactly that value. So the output is the input if it's positive. So this is basically just y equals x. So here this should be 0.5. Here would be approximately 1. That's obviously 0 here. This would be x. This axis would be the sigmoid function of x. This would be the hyperbolic tangent function of x. This is 0. This would be 1. Here would be -1. Here would be 0. Value of x and x. So let's note down the equations. So the sigmoid equation is in a simple form 1/1 plus e to the power of -x. So what happens if we plug in the first value, which is 1? That would be equal to 1/1 plus e to the power of -1. and that is approximately 0.73. Now let's plug in the second one, which is sigmoid of -2. That would be approximately 0.12. Let's do 0. And now what can be seen here is that if we use this sigmoid function as the activation function of the output unit, then we can say, let's use it as a, or let's use the network to classify a binary target. So is it either 1 or 0? And if we have this value, then we would say, well, this could be, let's put in a threshold of 0.5, and then this would be a classified as 1 in this scenario, and this would be classified as 0. So in a binary classification between 0 and 1, and this would be exactly on the threshold. So I think this would still be classified as a 1, but yeah, that depends on how you define the threshold then. But basically, this is how you can use this to get this binary classification in the end, because you have values between 0 and 1. Now, let's have a look at the hyperbolic tangent function. So it's e to the power of x minus e to the power of minus x divided by e to the power of x plus e to the power of minus x. Now let's just plug in some the values. So 1, for example, that would be e to the power of 1 minus e to the power of minus 1 divided by e to the power of 1 plus e to the power of minus 1. And that would be roughly 0.76. So it's quite similar to the sigmoid function, but maybe more. So this would be even closer to 1. So it would be, let's say, more confidently classified as 1. For if we did a binary classification. So if we plug in -2, then it would be minus 0.96. And now we have to think that we won't classify y between 0 and 1 binarily, but y between -1 and 1. That's that one you have to keep in mind. I think it was the same for the support vector machines, where we don't classify between 0 and 1, but we classify between -1 and 1. So that's how we have to label our targets. And now the value, or no, we have to still plug in 0. And that's pretty easy, because this would be e to the power of 0 minus e to the power of 0 and divided by e to the power of 0 plus e to the power of 0, and that is obviously 0. And now the value function is basically this max operator. So whatever is bigger, 0 or x, will be the output here. So value of 1 would be positive, so this would be 1. Value of -2, that's negative, so whatever negative it would be always 0. And then value of 0 is also, like, it wouldn't matter if it's x equals to 0 or 0, it's still 0. And yeah, so that would be the output for the rectifier here. Now let's talk about why do we actually use them. So especially the rectifiers, or the value function, is used a lot for the hidden layers. And that's and if we use a activation function for the hidden layers, then it's used to have non-linearities within the network. Because if we wouldn't apply the activation function, then it wouldn't matter how many layers we would put in the network. It would be still just a linear combination of weights and inputs. So we wouldn't infuse any kind of nonlinearities into the network, so we couldn't transform them in any way non-linearly. It would be always kind of either we could only add things up, so it would still be just a linear transformation. So that's basically the way, through these activation functions, we add nonlinearity to the network. And then in the output layer, if we use a activation function for the output layer, we want to have to transform that output, for example, for a binary classification, then we could use the sigmoid or the hyperbolic tangent function. If we would have a regression where we want to have a continuous output, then we wouldn't use any output activation function. So the output of the activation function would be just passed without any activation, and the output of the output unit would be passed without any transformation by the activation function. Or if we, for example, have a multifactorial target, so we have 10 classes or so, then we would use a softmax activation function there to classify or to calculate probabilities for every class. So these are the two reasons why we use activation functions: is introduce nonlinearity to our network, and second, use it for classification at the output unit. And that's basically where the magic happens. So this is how the neural networks have gotten their fantastic results in the last years. So obviously there were also other kind of inventions like convolutions, but the reason why they are more popular than they were in the very beginning was these activation functions.